Okay, can you hear me all right? Okay, perfect. Hi, I'm Tosca. I'm presenting joint work with Shai on fair learning for, on representation learning for multitask learning and the inherent limitations of this approach. So, as many of you are probably aware, in the last few years, there have been more and more examples in many different domains on how classifiers that were produced by some machine learning tool, which performed well on some in terms of accuracy on some training distribution, discriminated against some subpopulation in deployment. So this, of course, is a huge problem, and thus the field of fairness in machine learning has emerged. And there have been many different tools that have been proposed to deal with this issue, and one of them has been representation learning. Representations are, of course, very nice for machine learners because one can hope that they can be reused for different tasks. So in this work, we ask whether representation learning can help to achieve fairness for multiple tasks. We are, of course, not the first people to ask this question, and there's been a long list of papers, starting with Samuel et al. At ICML 2013, which propose algorithms to come up with representations that that aim to provide guarantees for fairness for downstream tasks, and this should hold for any downstream task with possible change of distribution and for all kinds of uses of this representation. So in our work, we show that if this goal this generally, as it has been in the literature, this goal is not achievable. So we look at a binary classification setup, and the running example will be job application. So we have some domain X, which represents the population, and some binary label space, and this binary label space corresponds to an accept-reject decision, and it can also be interpreted as a threshold on the performance of applicants in the ground. We can partition, or we assume that we can partition the domain X into two subpopulations, group A and group D, where you can think of A as an advantaged group and D as a disadvantaged group. However, we deal with those two populations symmetrically in our work. Now we have a set of tasks which are given as distributions over X cross 0, 1. So those are the distributions P1 to Pk. Now the goal of fair representation learning is to domain X to some latent representation, and then the classifiers for each task are trained on this representation. So one can think of this this mapping either from a data collection standpoint. So there's a lot of regulation, for example, that tells you which kind of questions you are allowed to ask for job applications, so that limits your representation. But one can also think of this as a learned representation that potentially hides some information about individuals. So now we have to talk about what we mean by fairness. And there is, of course, no unique answer to what fairness is, and there's still a lot of debate in the community. And sometimes the values we have are even contradicting each other. However, in here we will look at statistical notions of group fairness, which assess a discrimination on a population level. So just to say, this is what we mean by fairness now. Of course, there can be more debate. And the most common notion of group fairness is demographic parity, and this just says that a classifier has demographic parity fairness if its classification outcome is statistically independent of the group membership. This is with respect to some marginal distribution. In many works, it's not been discussed what this marginal distribution should be. Usually it's the test distribution is the distribution used. So in our scenario, this would be the number of, or the population of applicants we get. And in this work, we will also just assume from now on that we take the test distribution as this marginal distribution. However, in real-world scenarios, it might be worth discussing what the relevant distribution here is, whether it's demographic of a country or a city, rather than just the applicants that you see. Another problem of demographic parity is that there could be a correlation between the group membership and the ground truth label. And to deal with this issue, there has been this notion of equalized odds. People proposed this notion of equalized odds, and odds now proposes that the group membership and the classification outcome are statistically independent given the ground truth label. And this is equivalent to saying that the false negative rates and the false positive rates between groups are the same. Now, how do we want to measure the fairness of a representation? We take a modular approach here. So we say that we are only interested in the outcome of the learning procedure, and then we can measure the fairness of the classifier that comes out of that learning procedure. So now we can distinguish different scenarios on that depend on who uses the representation. So the first scenario, the first motivation is that of a regulator. As I hinted before, there's a lot of regulation or laws that say what kind of features you're allowed to use for decision making. So in here, a regulator would want to prevent discrimination independent on who uses this representation. So we have to assume an adversarial, even an adversarial agent who might actively want to discriminate. So in this scenario, for this scenario, we came up with the notion of adversarial fairness is the most appropriate. Fairness representation is called adversarially fair for a distribution and a fairness objective if every classifier that can be defined on top of this representation is fair with respect to the objective and the distribution. A different scenario is the setting in which we have practitioners who want to mainly optimize for accuracy. They care maybe a little bit about fairness, but they don't want to put a lot of effort into training fair classifiers. So they have a data curator who wants to make a representation that can be then used by practitioners who optimize for accuracy. In this scenario, we don't need to guarantee that we get fair classifiers for that every classifier on top of this representation is fair, but rather we can restrict ourselves to the base optima, to requiring that the base optima classifier is fair, or possibly also saying that we want optimal classifiers to be to fulfill some fairness requirement. And while we will now only talk about the first scenario, we think it's important to say that there's a distinction that should be made in the literature, and especially when one decides to motivate fair representations in a certain way in the introduction, the evaluation should match that. So if one says that a representation guarantees fairness for downstream tasks, it's important that then the evaluation just evaluate the classifiers you get if you optimize for accuracy on that representation. But you need to check that even if this representation is used adversarially, then you still can get fairness guarantees. So now to get a bit of intuition of how fair representation can work, We now look at adversarial fair representation for demographic parity. So here we have a population of applicants, and we can assume that their features have been discretized in some way. Now we can look at classifiers that can be built on top of this. If we now have a representation that has for every feature vector an equal amount of population A and of population D, then we basically hide the group information in this representation, and every classifier that can be built on top of this fulfills demographic parity fairness. So this was the initial approach. However, if we now assume that there is a distribution shift, which could be quite common in reality, so for job application, you could just have this same job with the same qualifications, but in a different city, then we get a distribution shift, and now the fairness guarantee does not hold anymore. So, and in fact, the more fine-grained the representation is, the more vulnerable it will be to distribution shifts. So after distribution shifts, the classification rules are no longer fair here. And this motivates our first theorem, which says that no data representation can guarantee demographic parity fairness for any downstream tasks. And we can say that any non-constant representation, we can come up with a distribution under which this representation is arbitrarily unfair. And this is on how much training data you have. This is just a fact about the distribution. We also get a similar result with respect to equalized odds fairness. In here we have in here we can either say we get both results. We can say that if you have tasks with the same labeling function and shifts in the marginal, then you can get arbitrarily unfair due to a shift, but also you can say the marginal stays the same in labeling function, so maybe the qualifications between jobs change, but you have the same kinds of applicants. Then you can also get arbitrarily unfair. So in general, we see that for any representation, there is a downstream task for which this representation does not prevent unfairness. This is, of course, a worst-case analysis that answers questions in the literature, but we can now maybe try for a less ambitious goal and say maybe we have a fixed set of tasks that are in some way related, and maybe we can find a useful representation that guarantees fairness for all of those tasks. And by useful representation, we mean that the representation allows for perfectly accurate classification. And here we also find a negative result for equalized odds fairness. So roughly speaking, say that for any two tasks, there is no representation that is useful as well as fair with respect to both of these tasks. So in detail, for any two different tasks, P1 and P2, which share a marginal, and where at least one of them has some correlation with the group membership, and those tasks need to be different. For two of those requirements, there is no representation which is adversarially fair with respect to P1, adversarially fair with respect to P2, and rich enough to allow for accurate classification for both of them. So this is our main result, showing that at least if we look at adversarial fairness and equalized odds fairness, fair representation for multiple tasks is an inachievable goal. So this is the conclusion. The main is that there is no representation that can guarantee fairness for all downstream tasks. We think it's important that if people come up with representations, that they are specific about how this representation is supposed to be used, for what kind of distributions, for what kinds of agents. We think that if the goal of regulation is to achieve some statistical fairness goal, then regulating just the representation is not effective. It might still be the case that fair representation is useful as a tool for machine learning practitioners, but people should be precise about their claims. And lastly, we started some discussion on like what the relevant distribution is for statistical fairness notions. Yeah, that concludes my talk. Thank you for your attention, and
Any questions?
So you mean? Sorry. So the question is how to prove that there is no representation for any downstream task that is fair for any downstream task, right? So do you mean theorem 1 here? Okay, so in here we just come up with some distribution that is just come up with an adversarial distribution shift that affects one feature as one group on one feature vector way more than on the other feature vector. So we just need a distribution. So we just need to show that one classifier is unfair, right? So we just have one classifier that labels one part of the distribution as positive and one as negative. You can have a distribution shift that just puts all the mass of group A to the one cell and all the mass of group D to the cell that you label as 0, and then you have an no, oh yeah. So or do you mean this theorem? That's a more. Okay, so we just come up with a counterexample that's pretty trivial. No, you just said assume that there is one representation that is not constant. Then it allows for one non-constant classifier, and then for this classifier I can come up with an adversarial distribution.
Any other questions? Maybe I have a question, sorry. So the proofs are like worst case scenario. I'm wondering if you relax, so in, for example, I think it was theorem 3, the representation gives you 0 error. If you assume the error is bounded by epsilon, do you think there is any hope to find representations that would be fair?
I think that if you say, so you say you allow for epsilon unfairness, basically.
Right? I was thinking of error in terms of accuracy. So instead of assuming you can achieve perfect accuracy on the task, you assume like, okay, my error on the task would be bounded by some epsilon. Would that buy me anything so I can get fair representation?
I think this depends on how dissimilar the tasks are. So if you have tasks that only differ by epsilon in some measure, then both, like you could come up with a representation that is fair with respect to both. But in general, I think one can, like if epsilon is small enough and that the tasks are different enough, then one can come up with a quantitative statement.
Thank you. Oh, there's a question in the chat. Sorry. I don't see it.
So how about a function that maps everything trivial to 0, which should be fair though useless?
Yes, exactly. That is true. So I didn't but this theorem states it, that if we have a constant representation, then this representation would be perfectly fair. But as the person who asked the question points out, this is useless, and as soon as we have two, if we can distinguish two features, we are doomed in terms of fairness.
Let's thank the speaker again.